last talk of the first session is given by Elias Storme. No, it's Dominique Devriese, who is talking to us about secure calling convention for CHERI capability machines in practice.
Hi. Yes, so hi everyone. My name is not Elias Storme, so I'm Dominique Devriese. Yes, apologies. Elias is supposedly at a wedding somewhere and was unable to give the talk, so I am filling in. I should start by a disclaimer. So when we decided to submit here, we were not yet aware of that there was a different interesting workshop very related to these things. So at some point we decided to just submit to both places. If you are one of the unfortunate people who have attended both, then I apologize, but I hope there's not too many of you. So what I will talk about is a much narrower problem than what Peter has been talking about, but I hope still interesting.
Possibly soluble.
Possibly, yes. Let's take a look. It's definitely not a solved problem. It's a work in progress, as you will hear. So first, this is about CHERI capability machines, which I hope some of you are aware of. To give you an idea of, for those of you who don't know what that means this is a class of instruction sets that offer a very nice, if you ask me, a very nice type of security primitives, very different than hypervisor machinery and page tables and so on. What you get instead, or sometimes in addition, like on CHERI, is a notion of capabilities. So what is a capability? You can think of it as a fat pointer. So a pointer that doesn't just point somewhere in memory. It still points somewhere in memory. There's this cursor position. But additionally, it has some bounds information. So there's every capability comes with a lower bound and an upper bound. And that tells you which part of memory you can use this capability for addressing. So if you try to use the capability to read or write somewhere else in memory, the processor will tell you that's not allowed. Capabilities also have some permissions that tell you whether you're allowed to read or write or execute. There are some other permissions that are not less relevant for this talk. So benefits, you get some very sort of fine-grained way to enforce memory safety. And the hardware sort of does it all in the background. While your code is executing, the hardware is continuously checking all sorts of memory bounds on your memory accesses. And hardware people are able to do this very nicely in parallel with the actual execution of your code. So you pay relatively little for all of this hardware enforcement of memory bounds. You can actually use this essentially for two things. You can use it to enforce spatial memory safety. If you have an array and you try to read from it, that transparently the hardware will check that you're reading inside the bounds of the arrays, not outside. And that gives you a way of sort of a kind of sanitizer on steroids that runs sort of during the actual execution of your code. A second, and maybe a more important usage of capability machine primitives is for doing software compartmentalization. So if you have a software system, you can sort of chop it up into pieces, give access to some parts of memory to component A, give some other component access to other memory, etc., and then have some sort of a context switching, but a very cheap form of context switching when the components invoke each other. An important question is how fine can we make this compartmentalization? What are the components? If you have a browser, maybe every tab is a component. The CHERI people have demonstrated nicely that this is possible. But what if we want to go further? What if we want to make if we have an object-oriented application, maybe we want to make every individual object a compartment. Or if we're writing in a functional language, maybe every closure should be a separate compartment. And that means there's a very big amount of compartments, and you need to make compartments cost very little, right, to make this feasible. On CHERI-BSD, that's currently not the case. So particularly every compartment on CHERI-BSD has its own stack, and the stack needs to be a certain size to make things work. So that means you cannot make compartments too small because you're going to have to reserve a lot of stacks, and that's going to cost way too much memory. The compartments communicate through a trusted intermediary that is going to switch stacks when you switch from one compartment to another. What we're interested here in this work is, can we get rid of these separate stacks? Can we give all compartments, can we make all these compartments share the same stack in a secure way, so that one compartment isn't able to access the stack frames of another? And that would allow, we hope, a more granular compartmentalization, faster communication between compartments. So there's two things you need for this. So first, and I will talk about both, you need a return encapsulation. When you create a return pointer, you need to somehow encapsulate that so that the callee isn't able to use it in a way that he or she shouldn't be able to. And second, you need to do stack revocation. So once, when you give a stack pointer or a return pointer to some callee, the callee returns, and then you invoke another callee a second time, that old stack pointer and that old return pointer should no longer be usable, right? And if you don't do that, then you're going to get into problems. So let me focus a bit more. So return encapsulation. Imagine we have a stack growing downward. We have a caller stack frame over there. So when you do a call, you're essentially you're giving some authority to the callee. Essentially, in this case, that means you're giving the callee access to whatever remains of the stack after you sort of reserve your own part. When the callee returns to you, you want somehow to get back your original authority, including your own stack frame. But you don't want the callee to have access to that. So you need to create a return pointer that somehow reestablishes your authority for your code without the callee having the ability to do that. A second problem is stack revocation. So when your callee has returned to you, you want to be sure, so you want to be sure that old return pointers, old stack pointers are no longer available. And this is particularly hard because the callee has the ability to store capabilities all the way down in this stack, right? There's relatively easy ways to prevent the callee from storing capabilities elsewhere in the stack, elsewhere in memory, I apologize. However, in this, it's very hard to prevent them from storing something in the stack because they're going to get access to that part of the stack again when you invoke them the second time. Okay. So this is a bit technical. I hope the explanation is more or less clear. One way to do this is by clearing a lot of stack memory, which actually happens in some systems, like Chariot, I'm not going to go into too much details on that now. What this talk is about is there's a number of theoretical proposals from some of which I was involved with myself, not all of them, particularly building on linear capabilities, local capabilities, uninitialized capabilities, directed capabilities, all different kinds of proposed variants of capabilities, particularly to make it cheap to do this revocation, to somehow prevent a callee from accessing what was in the memory in a previous invocation of the callee. Okay. So these proposals are all very formally sound, but very far away, but still a bit far away from reality. They are They often use, they typically use a sort of theoretical capability machine that has abstracted away from some of the realities of real capability machines like Morago, like CHERI-RISC-V, etc. And that's the topic of this talk. So can we make these sort of theoretical proposals more realistic? And particularly, we do three things to try and get closer to that. We have worked, on the one hand, there's an issue between applying these proposals in the presence of something called capability compression. I will talk more about that. There's an issue, of course, you need to implement them. So, in particular, I will talk about an implementation in LLVM that we have made of this. And then finally, we are doing some benchmarking to see how costly these proposals actually are in practice. So, capability compression, what do I mean by that? So this is a feature of CHERI. So if you do capabilities naively, then on a 64-bit machine, your capabilities will be 256 bits because you have to keep track of 3 addresses, lower bound, upper bound, and an intermediate address, and then some more permission stuff, which is too large, too costly, has a lot of impacts on the performance of caches and so on, and apparently for hardware systems people, this is just too much. For that purpose, CHERI uses something called capability compression, which essentially is a sort of lossy compression of capabilities that saves memory, but at the same time makes capabilities less precise, and this breaks particularly the secure calling conventions that I mentioned. Second, implementation in a mature C++ compiler, and finally the benchmarking. Let me go into a bit more detail. Capability compression. So there's a very clever compression scheme used in CHERI machines. There's, as far as I understand, several variants of this, but they all sort of have the same principles. They represent capabilities in a sort of floating point encoding, where the 3 addresses share some sort of common parts, like the exponent is shared, this exponent here is shared between the lower bound and the upper bound, etc. You can save a lot of bits that way, but it has certain consequences, particularly, essentially, the bigger your capability, the coarser the bounds need to be aligned. Okay. Why is that an issue? Because these theoretical calling conventions, they ignore capability compression. And that conflicts with an important operation that happens all the time in those conventions, namely stack splitting. What does that mean? We have a stack pointer pointing from there to there. We want to invoke a callee, and that means we need to split up our stack pointer precisely at the boundary between these two stack frames. However, the stack, as you can imagine, it should be quite big. If you want to split precisely at this point, it's not going to be very well aligned, and that means that is essentially a sort of fundamental conflict between the two approaches. If you do some calculations, then if we want, since we can only assume that the split between the stack frames is going to be 16-byte aligned, that means the maximum stack size we can support is 16 kibibytes, which is way too small. If you look at Linux, for example, default stack size is 10 mebibytes, so a lot bigger. So we are proposing a solution here, which is to split up the stack into 2 parts, something we call an active stack, something we call a reserve stack, where the reserve stack is much better aligned, but the active stack is sort of the stack that you're using in one stack frame. There are some issues to make this work, but you can read a bit more about that in the paper. Particularly, at certain points, we need to replenish the active stack, which means turn this sort of active stack that is smaller than a certain limit into a a larger version by taking some authority from the reserve stack, putting it in the active stack, and continuing. Okay. Some considerations that we haven't solved yet, or where we have some ideas but which we still need to sort of validate and test and so on. Where should this reserve stack capability be stored? Current ideas just at the bottom of the active stack. Can components share this replenishment algorithm? Do we need to duplicate it in all components? We think so, but practical consequences need to be investigated. Compatibility with stack objects, there's a certain issue we need to take care of, that we don't accidentally replenish stack objects rather than, but we only do that for the stack pointer. There's a certain case where this can happen. And then finally, where and when do we need to check whether replenishment is necessary? Our current idea is to do this by the caller on every call. So all of these things need to be validated, but we think we can make this work. Second contribution in this work is an implementation in LLVM. So why do we want to do this? We want to investigate in practice these theoretical calling conventions. Can we make this a reality? Can we benchmark them to actually see how costly these things actually are? And also compare. Maybe if we don't just want to implement these different calling conventions, we also want to have sort of partial implementations that implement parts of the measures of certain calling conventions so that we can sort of quantify the individual cost of each of the sort of partial measures so that we can maybe see where some improvements are still needed. Why LLVM? LLVM is quite standard for CHERI, and LLVM is quite mature, so we can benchmark on sort of hopefully on real C and C++ code. There's two orthogonal components, this return encapsulation and stack revocation, and that actually means we can investigate several options for both of these components. For the return encapsulation, we can essentially work with something called sentry capabilities or with indirect sentry, where we think indirect sentry has certain advantages, but I won't go into detail here. So there's some detail here. Essentially, sentry capabilities require that for every encapsulated return pointer, the code needs to be stored close to the data that the return pointer carries, which is annoying. Essentially, it means you need to store some trampoline code on the stack, which systems people don't like, etc., etc. So indirect sentry capabilities should allow us to do better. Stack revocation, there as well, there's many options. We can work with local capabilities and stack clearing. We can work with alternative proposals, for example, uninitialized capabilities, which we have proposed in collaboration with some people in Aarhus. And there's other proposals that we might want to look into. An uninitialized capability essentially allows you to represent ownership of a certain region where you have read and write access to some parts, but only write part to some other part. And when you initialize this, you can sort of shift the bound downwards. So this is something that we have proposed, which works well in theory, which we want to investigate whether it can work in practice. So that means we have a sort of design space that we want to explore. We want to focus on these things particularly as stack revocation, no stack revocation, working with uninitialized capabilities or with local capabilities and stack clearing. Return encapsulation, we want to explore these trampoline and indirect sentries. Some of these are implemented, as you can see with the full circles, the filled circles, and some of these are on the agenda. For benchmarking, this is sort of work in progress. This is the part that is most work in progress. We want to benchmark a bunch of these variants, including these ones, but also sort of partially implemented versions of these ones to sort of quantify the individual, the cost of individual measures within these calling conventions. And for all of these calling conventions, we want to look at different metrics, not just execution speed, but also stack usage, how much stack are we wasting, for example, with this trampoline code, binary size, how much code do we need to generate to do, for example, this stack replenishing, etc. Compatibility, that's the hardest to measure, but compatible are these calling conventions with sort of standard C idioms or widely used C idioms? How do we measure that? Currently, we're working with a sort of random testing framework, which focuses particularly on like functions with different signatures and with variadic arguments and so on. There's other things we would like to measure which are not covered by this testing suite, so we're still looking for other testing suites to also work with. We also want to get to sort of a real C code, but we're not there yet. Which hardware can we use? For many of these things, there's no hardware available. We can work with the SEO emulator, but it's not psychoaccurate. So we're looking at, for example, modifying a simple RTL implementation or working with a psychoaccurate simulator. Which software do we want to measure? Currently, micro benchmarks. We would like to get to macro benchmarks, but we don't know yet what is possible there. And that's it. So conclusion. We want to make these sort of theoretical calling conventions a bit more practical, or at least investigate how feasible that is, how advantageous that is, etc. And we are contributing towards that goal with these 3 different contributions.
Thank you, Dominique. All right. Are there questions from the audience, or are there people that attended the talk from the other workshop and remember those questions and want to ask them again? We are slightly over time, so we don't have much time for many questions, but yes.
It's a very small question, and the answer might well be no. I wonder whether for this last benchmarking point, whether you could do as well or better with less effort to, instead of making a Gem 5 version, which is a whole lot of work, capture detailed instruction traces and have a plausible cost model based on roughly Morello timing but different.
Yes, so exactly. So we talked about this with Robert Watson at some point, I think on Wednesday or on Tuesday, and he also suggested something along these lines to just have the SEO emulator, for example, just generate memory traces and then indeed infer sort of timings from some cost model, even a very simple one could give you a sort of rough idea of the performance you could expect in reality.
Or actually running on Morello, but with capabilities somehow managed around, so it wasn't in the way.
I am. Okay, another potentially good idea, yes. Apparently you can also use the Gem 5 cache simulator or the Gem 5 memory model without using the full simulator, so that's another option. So this is what we're investigating for the moment still.
Well, thanks again, Domi. Before you applaud, a couple of things. There's still a short talk session at the end of the 3rd session today, which is free. So please feel free to come up and present some short talks. I'm looking at you, Marco Vassen, I'm looking at you, Katalin. You're all welcome to come and present short talks. And remember, if you're the speakers from the next sessions, to come up and test your equipment. As you've seen, there's delays to be expected. Thanks again, Domi, and there's a break now.